Hello and welcome to this lecture on dynamics. In the last class we looked at Lagrangian Euler dynamics and we saw how to compute the joint torques given the velocity at the joints. Today we'll continue our discussion of dynamics and we'll look at Newton-Euler dynamics. Now like kinematics, where we have forward kinematics and inverse kinematics, in dynamics also there is forward dynamics and inverse dynamics. Okay, so today we'll also look at that and then proceed to look at our Newton-Euler dynamic equations. Now in dynamics it's always very important to ask this question, that which is more efficient. So we'll look at the efficiency of Newton-Euler and Lagrangian Euler dynamic equations. So today we'll be discussing about Newton-Euler dynamics. First, a very quick recap on what we did in the last class. So in the last class we talked about Lagrangian Euler dynamics, and we said that Lagrangian Euler is basically an energy based method in which we find the Lagrangian Euler is essentially an energy based method, and in this energy based method we compute a scalar function which is called the Lagrangian, which is the difference of the kinetic energy minus the potential energy of the links. Then we put in the equation d dt of dl by d theta dot minus dl by d theta is equal to tau. Okay, and we can simplify this by writing that it is d dt of dk by d theta dot minus dk by d theta plus du by d theta. Sorry, we are writing ke. So is equal to tau. Okay, where u is my potential energy and k is my kinetic energy. Okay, so this also I can write it as k minus u. Okay, so what we can do is in the last class we solved the problem where we looked at a manipulator which had a prismatic joint, and then it had a revolute joint. Now very quickly going back to that, so we can go back very quickly to that problem which we solved in the last class, and it had a structure of the manipulator was something like this. There was a revolute joint here. This is my Z0, Z1, Z0, Z1 axis. Then there was a prismatic joint here. Okay, this was my prismatic joint. So theta 1 is the variable here and d2 is the variable there. Okay, please refer to the last class. M1 is the mass, M2 is the mass here. So please refer to the last class notes in the last class lecture where we derived the equations. Today I'll just write out the final terms and then we will proceed. Now when we found the kinetic energy and the potential energy, we found something which was very interesting here, and that is that the joint number 2, although it's a prismatic joint, that means it moves like this. Okay, it's prismatic, but because the previous joint is a rotating joint, when the previous joint rotates, it subjects the next joint, the prismatic joint, also to velocities, linear velocities. Okay, so that is something that we found interesting, that in dynamic equation the velocities propagate from joint to joint. Now we derived the final equation, and our final equation came out of the form m. So tau 1 tau 2, if I'm writing it in matrix form, tau 1 tau 2 is equal to the inertia matrix, which is equal to m1 L1 squared plus IZZ1 plus IZZ2 plus M2 D2 squared, and that is 0, and that is M2. And at the bottom there is 0 and M2. So here we have theta 1 double dot, and here we have D2 double dot. So this is my inertia term, plus we have the Coriolis and centripetal terms, D2 theta 1, sorry, D2 dot and theta 1 dot comes in there, and it is minus M2 D2 theta 1 dot squared. Okay, and finally we have the gravity term, which comes out to be M L1 plus M2 D2 into g cos theta 1, and the second term is n2 g sine theta 1. Okay, so please refer to the previous lecture, that how did we derive and how did we get these terms. So in the previous class, I derived it as tau 1 is equal to something, the equations, and tau 2 equal to, we derived it this way. Now I'm writing it in matrix form, and it comes out to be like this. Now what we see is tau 2 is equal to, this is the inertia matrix into acceleration, theta into acceleration. Now acceleration is theta 1 double dot and d2 double dot, because there are two joints, so the acceleration, one is a linear, one is an angular acceleration, the other one is a linear acceleration, okay, depending on whether it's a rotating joint or a revolute joint. The second is Coriolis plus centripetal. Okay, this is the second term, which is here. Okay, and then the third term is, of course, gravity term. Now we can see that this depends on theta double dot and d double dot, d2 double dot, theta 1 double dot. This depends on theta 1 dot and d2 dot, and the last one depends on theta 1 and d2. Okay, so this shows that the total torque is the sum, is because of the inertia term, which depends on acceleration, Coriolis centripetal, which depends on the velocity, and the gravity term, which depends on position. So the total torque, the total equation in general form is written as tau is equal to, so this is the very general way of writing, m into theta double dot plus v into theta dot, okay, plus g into theta. So all the terms that come can be put under each of this, depending whether they depend on acceleration, velocity, or position. And this is my total equation. So the equation, the dynamic equation, is written like this. So now we see that we can have two done, like your kinematics. So we had kinematics, we had forward kinematics or direct kinematics, and we had inverse kinematics. Now forward kinematics is you're given theta and you want to find what is xy, the end effector. Inverse kinematics is you're given xy, okay, so this is the input and you want to find what is theta. Okay, so this is my forward kinematics and this is my inverse kinematics, right? So similarly in dynamics also we have similar. So in dynamics we have our forward dynamics, and our inverse dynamics, which is based on this equation. Okay, so our forward dynamics would mean, given tau, you find what is the thetas. So you get theta double dot, from theta double dot you can integrate and get theta dot, and then you get theta. Now in the inverse dynamics is you give acceleration, velocity, and position, and you get what is the joint torques. Okay, so it is using this equation, the dynamic equation, to get forward dynamics or inverse dynamics. So if you want to do forward dynamics, that means we need to find what is acceleration, then integrate, get position, and then get velocity. So today we'll see how do we do that also, because this is required for simulations, for simulating, okay, a robotic manipulator. This is what we need, right? So today we'll be looking at forward dynamics and inverse dynamics also. Now let us move on and now proceed to Newton-Euler. So what we have seen here is that our dynamic equation has a particular structure, and the terms depend on acceleration, velocity, and position. Okay. Now let us move on to Newton-Euler. Now Newton-Euler method is a force-based method, and it is basically considering Newton's formula and Euler's. So today we start with Newton-Euler. So Newton-Euler, okay, formulation. So in the Newton-Euler formulation, it is basically using Newton's equation. Now we know that we have a rigid body like this. This is a link, and the rigid body is moving. So this is my link, and this is my let's see, this is the the link is on this side. Now if this link is moving, okay, then we have to supply forces, right, to cause motion. So if there are forces being given in this direction, F, so this will cause an acceleration in that direction, which is v dot. So Fi we can say, and vi dot. Okay, so this is Newton's this is the force is equal to mass into acceleration. So the force here is equal to mass into Vc. Okay, mass into acceleration, right? So this is Newton's law. A link which is moving with a particular acceleration, we have to give a force. So this force is equal to mass into acceleration. Now, so this is one equation which we are using. Now, some things to note about that. Where is this force acting? This force is acting at the CG of the link. So this is my CG of the link. Okay, so that is to be noted. The next is Euler's. So we have the link again. This link is subjected to angular velocity and angular acceleration. Okay, so this is my link again, and this link now is subjected to, the center of it is subjected to a moment n, and this moment causes a angular velocity omega and an angular acceleration omega dot. Okay, so this is a rigid body subjected to a moment and which is having an angular velocity and angular acceleration. Okay, now the equation that defines this moment is n is equal to, again this is the CG of the link is equal to I into omega dot plus omega cross I omega. Okay, so this is the inertia at the CG with the origin of the inertia tensor, which is located at the CG of the link. That is why we are writing C, phi c. So this is my Euler's equation. So this is okay. So if we use Newton's equation and Euler's equation together, then we this dynamics is called Newton-Euler dynamic formulation. Okay, that's where the name comes from. So we have Newton and we have Euler dynamic formulation. Okay, so Newton-Euler formulation and Lagrangian-Euler we saw some time back, and if you see here, this is the force-based method. Now what this basically tells us here that you can understand very clearly is that we have to find the forces which are acting at the CG of the link due to accelerations. Okay, so we saw that when a link is moving, the velocities and accelerations propagate from link to link. Okay, so from the base link it propagates towards the forward link, and that acceleration and velocities will be acting at the CG of the link also. Okay, and based on that we can find what are the forces acting. Now once we get the forces acting, then we have to come backwards and say what is the torques acting at the joints because of these forces. So let me explain it like this, that we have a link. Okay, so we have a link here. I'm drawing three-dimensional shape, so it is generalized. There is a link here and there is a link here. Okay, so this is my link structure, and we are saying that there are forces and moments which are acting at the, so there is Fi and then there is Ni acting at the joints. Now on the CG of the link there is a moment, okay, capital N, and there is a capital F which are acting at the CG, and there is on the other side on the next axis, so my axis is here, so on the next axis we are having Fi plus 1 plus Ni. This is something we have seen. So Fi plus 1 and Ni plus 1. Okay, this is one equation. So what we have seen is that this is the force exerted on link by the other link. Okay, so we have my axis here. Okay, so now what we are saying is that let us look at the equations. Or before we go to the equations, let's look at let's try to understand this a little bit clearer. So this is my linkage. Okay, so there is a velocity here, theta 1 dot, theta 2 dot, like that. Now this will cause a velocity that side that we have seen. Okay, and this is going to propagate in the forward direction. Now what will happen is this velocity and accelerations which are there will cause a force to be acting on the CG of the links. This is the CG of the links. Okay, now because there is a force acting on the CG of the links, this force will actually come backwards and will get reflected onto the joint torques now. Okay, so there are two loops. Okay, this is called an iterative, this process is iterative. So Newton-Euler is an iterative method, okay, and there is an outward iteration, there is an outward iteration and an inward iteration, okay, outward and inward iterations. What are the inward and outward iterations? What is the outward iteration? This is the outward. So when the links are moving, the velocities and accelerations are propagating outwards. Outward, why the name outward? So from frame 0, it is going to frame n, so it is outward iteration. Now this is going to cause, using Newton's law and Euler's equation, we can find what are the forces acting at the CG because of this velocities, right? And once we get the forces which are acting, we know what is the joint torques being caused by those forces. Now that is my inward iteration. So this force which is acting here, okay, this force is going to come backwards and cause a joint torque, and this is my inward iteration now. Okay, so there is an inward iteration. So there are two iterations. One is to compute the velocity propagation and acceleration propagation from link to link, okay, both angular and linear, and then find what are the forces acting at the CG of the links using Newton's law and Euler's law. And then based on those forces acting on the CG, we have an inward iteration which is going to tell us that what is the joint torques because of the forces there. So this is the basic equations. Let's write down the basic equations. We saw the velocity propagation in the last class. I think when we talked about velocity and static forces, we looked at the velocity propagation. Now let us look at the acceleration propagation. So let's first look at the outward iterations. Okay, that means from frame 0 to frame n, how the velocities are moving outward. So to go from link to link, we get I plus 1, I plus 1. I explained that I plus 1 basically means it is going outward. Okay, so this means that the rotation matrix is the inverse. Okay, so let me go back and explain that again. So here this is going outward. Okay, so this means that I'm using an inverse rotation matrix, which is the transpose. Okay, because the rotation matrix relates the rotated system to the base system, whereas here I'm doing the reverse. Now, so this is equal to Wii plus theta I plus 1. Okay, dot. This is always towards z, so I'm not writing z, but the axis is always z-axis. Theta is always around z-axis. Okay, that is something to remember. Now, what about this is velocity? Now, by differentiating this, I can find out with respect to acceleration, which is equal to dot is equal to r I plus 1 I omega I dot plus r of I plus 1 I omega I cross theta I plus 1 dot plus theta double dot theta I plus 1 double dot. Okay, so I'm leaving the z. Please note that theta I plus 1 is along z I plus 1. Okay, this is the rotation about z axis. So these are all rotations about z, so I'm leaving this z out, but please note that there is a z there. So whenever I'm writing theta dot, it is about the z axis. So this is my velocity, angular velocity, this is angular acceleration. Now the linear velocity is equal to vi plus 1 dot, so again I plus 1 to I plus 1 is equal to I plus 1 r I. This is equal to omega I dot cross pi plus 1 I plus omega I cross pi I plus 1 plus VII dot. Okay, so what we saw is that the velocity propagation depends on the velocity of the previous link, okay, plus the velocity because of the rotation of the previous link, the linear velocity because of the rotation, which is this term, okay, and this is the velocity of the previous link. Now that is the acceleration, the linear acceleration. Okay, so we have computed velocity, Okay, angular velocity, angular acceleration. Then we have computed linear acceleration. Now we are interested in finding the velocity at the CG of the link. Okay, so the forces are going to be produced at the CG of the link. So what we do is we convert this to the CG of the link, which is equal to omega dot I plus 1 cross pi plus 1 pc I plus 1. The previous one, please note, it is pi plus 1. Here it is pc, means it is the term which is where pc is the distance, where pc is the, sorry, let me write this here, this is not correct. This is pc I plus 1. So pc is the distance to the center of gravity. So please note that I plus 1 omega I plus 1, and this is cross of omega I plus 1 cross pc I plus 1 plus vi plus 1 I plus 1 dot. Okay. So in the couple of classes back, we looked at the velocity propagations. And if you take those equations and differentiate them, we get the acceleration, so linear acceleration and the angular acceleration. Now, the linear acceleration, we found this is for the joint, whereas this one is for the CG. Okay, so this one is a VCI plus 1. Okay, please note this. So this is the acceleration at the CG of the link, and PC also stands for the distance to the CG of the link. Okay. Now, so let me just go back. Yeah, so this is my PC. So this is my PI plus 1, and this is PCI plus 1. So this is the distance to the CG of the link. So please note that, because the forces are acting at the CG of the link. Now, once we have written the equations, we can use the outward iterations. We can write F I plus 1 is equal to mi plus 1 into Vc I plus 1 dot. Okay, so what we are writing here is that the forces acting, okay, at the CG is equal to the mass into the acceleration, the linear acceleration. Okay, so this is Vc, so this is Newton's law. Now what is the moment acting? N I plus 1 is equal to I, so the inertia tensor with the origin at the CG, omega dot I plus 1 plus I plus 1 omega I plus 1 cross IC into I plus 1 into omega I plus 1. This is Euler. Okay, so we have two equations. One is Newton's, the other one is Euler. So one gives the forces acting on the CG, the other gives the moment acting on the CG. And we have computed the accelerations, the linear acceleration and the angular acceleration with the previous equations. Now, once we have done this, what we do is this is my outward iterations. So this is outward. Okay, so this is the outward iterations where we have got the forces acting on the CG. So this is my manipulator, and this is rotating, theta 1 dot, theta 1 double dot, theta 2 dot, theta 2 double dot. Okay, because of which, so this is going like that, outward. Now this is subjecting the CG to forces. So there are forces and moments acting on the CG. Okay, now the forces and moments acting on the CG are going to cause a torque now. That is my inward iteration. So the inward iterations are to find the joint torques because of the forces. Okay, so what will that be? So the force, the capital force which is acting at the CG link is equal to, will cause forces at the joints, is equal to I plus 1. This is equal to I plus 1 F of I plus 1 plus Fi. Okay, what is capital F? Capital F is the force acting at the CG, and this is the force at the next joint. So this is coming backwards. So what do I mean by coming backward is that the forces which are acting will come in this direction now. Okay, so that is why it is called the inward iteration. So this is the force and this is the moment. NII is equal to the moment acting at the CG plus I plus 1 R, I plus 1 and I plus 1 plus PI PC I cross Fi. This is something we have seen before also. Okay, plus Pi into I plus 1 plus R of I plus 1 into Fi plus 1. Okay. So this is the moment acting at the joint. So the moment is the torque that I want. So tau I is equal to NII into the direction is along the z-axis. So this is the direction. So this is the torque acting at the joint. Okay. So by using this forward and backward computation, we are able to find the torques acting at the joints. So again, let us look at an example where we are simply going to use this set of equations. Which set of equations? This one. So we have to start off with this set of equations. Okay, outward iteration first, depending on what is the joint velocity and accelerations, and then based on that we can find the forces acting on the CG of the links. Then once we find the forces acting on the CG of the links, we can come backwards and find what is the torques acting because of those forces. Okay, so this is the basic formulation. We'll use this set of equations one by one. Okay, velocity equations, we solved a problem a couple of classes back, I think 2 classes back. Today we are finding accelerations and we'll find forces. So this is an example of a closed form dynamic equation. So this is example of, let me draw the manipulator. So there is one link, there is another link there, and this is my theta 1, that's my theta 2. Okay, this is theta 2, this is theta 1 corresponding to my x-axis. Z-axis is this side, Z0, Z1, this is my x1. Okay, and there is a torque here, tau 1, and there is a torque there, tau 2. Okay, there are masses m1 and m2. Okay, so this is the basic problem. We have a 2-link manipulator which has links, which has variables theta 1 and theta 2, and they have masses m1, m2, and we are asked to find what is the torque tau 1 and tau 2 acting at the joints. Now we are using Newton-Euler. So something to note here is that we are using Newton-Euler formulation. So we have to first do outward iteration, then we have to do inward iteration. Now a couple of more things to note here is that the assumption that we are making here is that the mass distribution is extremely simple and the mass exists at a point mass at the distal end of the link. Okay, so we are making the mass distribution so the mass distribution is point mass at distal end. Okay, so this is the assumption that we are making to simplify everything. Now because we are saying the mass distribution is a point mass at the distal end, so what we can see is that the distance to the CG PC of the first link, for the first link P1 C1 is equal to L1. It is along the x direction. Okay, because of the assumption we made a point mass. Now the second is that we are seeing that the distance to the CG of the second link is also L2, which is the link length. Okay, because we are saying point mass. So basically I'm saying that there is a point mass here, this is my M1, and there is a point mass there, which is my M2. Okay, so this is my L1, that's my L2. This is the assumption I'm making. Now because of the point mass assumption, the inertia tensor written at the center for each link is the zero matrix. Now we are making the of this point mass. Okay, so my inertia tensor I C1 is equal to 0 and I C2 is equal to 0 because point mass assumption. Point mass. Okay, because of this. So please note this and please note this. Now the third thing is there are no forces acting there is no force acting. What are the other assumptions we are making? The other assumptions we are making is that there is no force acting at the end effector. So no external forces. So this means that F3 is equal to 0 and N3 is equal to 0. Okay. Now the base of the robot is not moving. This we know, base is fixed. So the initial velocities of omega naught of the 0 frame is 0, and the velocity and acceleration are both 0. Now there is another basic assumption that we are making. It's not an assumption. In the Newton-Euler equation that we wrote, if you note, okay, so when we go back here, if you note this set of equations, there was no gravity. Okay, so how are you going to include gravity? In case of Lagrangian Euler, we have a potential energy, so there is gravity, mgh. But here, where is gravity? Okay, so we need to include gravity. So how do we include gravity? We simply say that we include gravity forces by including the gravitational acceleration. Okay, so what we say to include gravity, so gravity included by saying that v0, the acceleration of the 0th link, is equal to g in the direction of y. Okay, so this is how we are including the acceleration due to gravity effect in this formulation. So if you look at this term, so we have x, y, z. So which is the y direction? This is the y direction. This y0. So we are saying gravity is acting in that direction, and that is my g. Okay, so gravity is included by saying acceleration is in the y direction. So these are some of the assumptions we have made, and we proceed to solve the problem from here. Now, what is the rotation matrices? The rotation matrix is Ri I plus 1 is equal to Ci plus 1, okay, minus sine I plus 1. Then this is sine I plus 1. This is a rotation about z. So these are also sine, cos, sine. And this is 0, 0, 1, 0, 0. Okay, this is 1. Okay. What is this inverse? Because I want I plus 1, r is equal to I plus 1 to I. That you would have noticed. So it is just the inverse of this. So it is Ci plus 1. This is Ci plus 1. So minus sine I plus 1. And this is sine I plus 1. This is 0, 0, 1, 0, 0. Okay. So now we have found the transformation matrices, and we have found the lengths to the center of gravity. There is no external force acting, so forces and moments at link 3 are equal to 0. The first frame is not moving. Sorry, not the first frame. The 0th frame is not moving. The base frame is not moving. Hence, we are giving angular velocity and acceleration to be 0. So in a moving system, for example, a space robot, then what we can do is the base frame can also have a velocity. But in our case, we are saying it is equal to 0. Okay. How is gravity being included? Gravity is being included by saying that there is acceleration due to gravity in the y direction. Now let's proceed and the outward iterations. So this outward iteration is essentially the effect of velocity and acceleration from link to link, propagation. So the first one is equal to theta 1 dot is equal to 0, 0, theta 1 dot. Okay. Now we are given that the variable is theta 1, so the velocity is theta 1 dot. Okay, so the first one, the angular velocity, is theta 1 dot in the z direction. What is the acceleration? The acceleration is omega 1 dot, which is equal to theta 1 double dot, which is equal to 0, 0, theta 1 double dot, theta 1 double dot. Okay, so simply by using those equations. What is the velocity of the first joint? Now note that there is the velocity of the previous joint, that is 0 joint, is 0. Okay, but sorry, the 0 frame rather, the 0 frame is 0 velocity. Okay, so but note that there is a gravitational acceleration. So v1 dot is equal to cos 1 sine 1 cos 1, 0, 0, 1, 0, 0 into this term. There is a g there, 0 g 0, which is equal to g into s1, g into c1, and 0. Okay, so please note that although frame 0 and frame 1, so it was something like this. So this is my first link, right? So my frame 0, z0, z1 is here, x0 is here, and x1 is here. Okay, so if you're seeing the origins are the same, and the 0th frame doesn't have a linear velocity, okay, and nor does it have an angular velocity, but there is an acceleration due to gravity in this direction. So why not there is a g there, and that is the one that is coming here. Okay, so v1 dot is equal to the acceleration due to gravity. Now what about, so this is the acceleration due to gravity which is acting on the first frame. Now what about the acceleration due to the forces, the linear velocity which is propagating to the CG of the link, that is equal to Vc1 now, okay, plus minus L1 theta 1 dot squared 0 0 plus GS1 GC1 0. Okay, so this is equal to, so we had the velocity of the frame, okay, that is essentially because there is acceleration due to gravity. Now when we are looking at the effect of this on the CG is at the distal end of the link, which is Vc1, and it is at a distance of L1. So what we are finding is the linear velocity of linear acceleration of that is theta 1 dot squared plus GS1. Okay, here it is L1 theta 1 double dot plus GC1, and this is 0. Okay, so how did we get this? We just have to go back to our equation here, okay, the equations that we derived, the forward and backward equations, and get it from there. So Vc1 is equal to this term. So there are 3 terms there. You can see one term is here, one term is here, and one term is here. Okay, so that is how we have got our velocity, which is the angular acceleration, which is acting at the distal end of the first link, which is given by this term. So we have found the velocity, and we have found the angular velocities and the linear velocity. Okay, now so what is the force acting? So we simply use Newton's law and say the force acting on the first link is equal to F1 is acting at the CG, okay, is equal to minus what was the mass, L1, so it is L1 theta 1 dot squared plus M1 GS1, and it is M1 L1 theta 1 double dot plus M1 GC1, and this is 0. So this is the force which is acting on the CG of the first link. What about the moment? N1 is equal to 0 0 0. There's no moment. Okay, so on the first axis there is no moment. Okay, and now, well, this is not first axis, there is a CG of the first link, this is the CG of the first link, force and moment at the CG of the first link, not axis. Now the outward iterations for so once we have done that, we find the outward iterations for link 2 now. What we get is link 2 velocity is equal to the sum of the velocity of the previous link plus its own velocity plus theta 2 dot. Okay, there is velocity propagation, right? So the velocity of the second link is equal to its own velocity, which is theta 2 dot, plus the velocity of the plus the previous link, which is theta 1 dot. So this is equal to, and then from here we get accelerations. So we get is 0 0 theta 1 double dot plus theta 2 double dot. Okay, so outward iterations for the second link is done this way. Then what we do is we have to compute the linear velocities. Now the linear velocities linear acceleration, is equal to C2 sine 2 cos 2. This is minus 0 0 1. This is 0 0, and then we get the velocity of the previous link. What was that equal to? Is equal to theta 1 dot squared plus g into S1 L1 theta 1 double dot plus g into C1 into 0. Okay, which is equal to, so this term is equal to L1 theta 1 double dot to minus L1 theta 1 dot squared C2 plus GS1 to L1 theta 1 double dot C2 plus L1 theta 1 dot squared. Okay, theta 1 plus, sorry, this is L1. So L1 theta 1 dot squared S2 plus G into 1 2. Okay, and that is 0. So this is the velocity of the, sorry, this is the this is the acceleration, the linear acceleration of joint 2. Now this is going to cause an angular acceleration, okay, at, so that's not VC, sorry, this is V2. This is going to cause angular acceleration at the CG, which is equal to 0 L2 theta 1 double dot plus theta 2 double dot, okay, plus minus L2 theta 1 dot plus theta 2 dot squared. This is 0 0 plus, you have to sit down and do this by hand. It's not difficult, but we just have to refer to those equations and just keep expanding them. That's all. Theta 1 dot squared C2 plus G into S12, and then the second term is L1 theta 1 double dot C2 plus L1 theta 1 dot squared S2 plus G C12, and this is 0. Okay. So we have got our acceleration. Now based on the acceleration, I multiply this with mass and I get the force acting on the CG. So F22 is equal to the force acting, which is M2 L1 theta 1 double dot S2 minus M2 L1 theta 1 dot squared C2 plus M2 G S12 minus M2 L2 theta 1 dot plus theta 2 dot squared. Okay, and the second term is M2 L1 theta 1 double dot C2 plus M2 L1 theta 1 dot squared S2 plus M2 G C12 plus M2 L2 theta 1 double dot plus theta 2 double dot, and the third one is 0. So this is the force. What is the moment? So N2 is equal to 0 0 0. Okay. So now what we are doing is, we have seen the forces acting on the CGs, and now next thing what we need to do is to find the inward iteration. So this was my outward iteration. Now I need to find my inward iteration for link 2 and then for link 1. So essentially we have found the forces. So this is my link. Okay, this is my link. We have found the forces acting there and the forces acting there. Okay, for the CG point of link 1 and link 2. So once we have got these forces F2 and F1, these forces are going to cause moments at the joints now. So next what we do is we do our inward computation for link 2. So we do the inward computation for L2 for link 2, and that gives us small f2 is equal to capital F2, and N22 is equal to, this is the moment acting at the joint 2, which is equal to 0 0, and here we get M2 L1 L2 C2 theta 1 double dot plus M2 L1 L2 sine 2 theta 1 dot squared. All you need to do is to just use those previous equations, put in the values, and we get the final torques acting, plus M2 L2 squared theta 1 double dot plus theta 2 double dot. Okay, so this is the torque acting at the second joint. Okay, now so this is the torque acting at second joint about the z-axis. So it is torque 2 actually. Okay, now what about the inward iteration for link 1? So inward iteration for link 1, what we get is F1 is equal to, F1 is equal to cos 2 minus sine 2 cos 2 0 0 1 0 0 into M2 L1 sine 2 theta 1 double dot minus M2 L1 cos 2 theta 1 dot squared plus m2g sine 1 2 minus m2 L2 theta 1 dot plus theta 2 dot squared is the first term. The second term is m2 L1 cos 2 theta 1 double dot plus m2 L1 sine 2 theta 1 dot squared plus m2 gc12 plus m2 L2 theta 1 double dot plus theta 2 double dot. Okay, and the last one is 0. So these are three terms. Okay, so the first term, second term, and third term. Plus there is one more term here. So the plus it is minus m1 L1 m2 dot squared plus m1 gs1, and we have m1 L1 theta 1 double dot plus m1 gc1 0. Okay, so it is this plus this. Now what we are seeing is that this is the force acting. What is the moment acting? Moment acting N1 is equal to, this is made up of three terms, 0, 0, and N is always about the z-axis, so it is m2 L1 L2 cos 2 theta 1 double dot plus m2 L1 L2 sine 2 theta 1 dot squared plus m2 L2 g cos 1 2 plus m2 L2 squared theta 1 double dot plus theta 2 double dot. Okay, this is one set. The second set is 0, 0, m1 L1 squared theta 1 double dot plus m1 L1 gc1. Okay, plus we have 0, 0, m2 L1 squared theta 1 dot double dot minus m2 L1 L2 sine 2 theta 1 dot plus theta 2 dot squared plus m2 L1 g s2 s12 plus m2 L1 L2 cos 2 theta 1 double dot plus theta 2 double dot plus m2 L1 g c2 c12. So this is the torque at the first joint, so this is also equal to torque 1, tau 1. So tau 1 is the joint, the torques acting at the first joint. So we have found the torques acting at the first joint and the torques acting at the second joint. Now if you write it in the form of the dynamic equation, the way it is written in terms of acceleration, velocity, and then tau 1 comes out to be equal to, tau 1 is equal to m2 L2 squared theta 1 double dot plus theta 2 double dot plus m2 L1 L2 cos 2 twice theta 1 double dot plus theta 2 double dot plus m1 plus m2 L1 squared theta 1 double dot minus m2 L1 L2 sine 2, and this is theta 2 dot minus twice m2 L1 L2 sine 2 theta 1 dot theta 2 dot minus m2 L2 g cos 1 2 plus m1 plus m2 L1 g c1. Okay, and tau 2 is equal to m2 L2 L1 L2 cos theta 1 double dot plus m2 L1 L2 sine 2 theta 1 squared plus m2 L2 g into cos 1 2 plus m2 L2 squared theta 1 double dot plus theta 2 double dot. Okay, now you can see that the torques depend on acceleration, they depend on velocity, theta dot, and they depend on position. Okay, so you can find the terms that are there are depending on acceleration, they depend on velocity, and there are also position terms, which is the sine theta 1 plus theta 2 and cos theta 1. Okay, so our dynamic equation basically is written this way, and this is the way that we now you can also understand why in the textbooks and whatever I have done is only done for 2 degree of freedom system, because if you try and do for 6 degree of freedom system, okay, you'll make a mistake and it will be extremely cumbersome. It's not that it's difficult, it's just cumbersome. The expressions are so long, so there's a high chance you'll make a mistake. So this is not done by hand, it will be done by a computer program. Okay, so 6 degree of freedom, manipulator, inverse dynamics or forward dynamics is not done by hand. and we would normally write a computer program which is going to do this. Now let's look a little bit further about the dynamic simulation. So if you're talking about dynamic simulation, this is used for simulating the robotic manipulator. So we have taken our dynamic equation tau is equal to m into theta double dot plus v into theta theta dot plus g, and if there is an external force, then it is okay. So this is external force. Okay. Now if you write it this way, then we need to find, for simulating it, you need to find the position velocity at every instant. Okay, so what you need to do is you need to find acceleration from here, and this is going to become equal to tau minus v theta theta dot minus g theta minus, there is a theta here, the theta minus f of theta theta dot. Okay. This is external force, friction, whatever you want to put, you can put it in there. Okay, and this can also be made equal to 0. Now so this is going to give us, you have to find theta double dot by integration. From theta double dot we can find theta, and then we can theta double dot we can find theta dot, and then we can find theta. Okay, so we can use numerical integration for doing this. Okay, so we can find we can use numerical integration techniques. Now one way is by the Euler integration. Okay, we can do Euler integration with conditions, the initial conditions of theta dot at 0, theta at 0 is equal to theta dot, and theta dot 0 is equal to 0. We can start from here and numerically integrate. T plus del t is equal to theta dot t plus theta double dot t into del t, and we can find that is velocity, this is acceleration, this is position, plus del t is equal to theta of t plus into del t plus half theta double dot t into del t squared. Okay, so we can find, by numerically integrating, we can find position, velocity, and acceleration. From the acceleration we can integrate it twice and get the velocity, and then we can get the position. Okay, so this is numerical integration. There are other techniques of doing numerical integration also. Now we can see that dynamic equation involves a lot of computation, so it is extremely difficult to do this in real time. Now this will be more important for our case in terms of control, because we said that a robot controller, what does the dynamics do? The dynamics actually disturbs the system. Okay, so this robot controller essentially has two inputs. One input, so the control system, if you are has independent joint control, which is the voltage which is going to the motor, and there is a dynamics which is tau. So it's a two input system, and in the two inputs, one input is the voltage which is going to the motor, and the second input is the disturbance torque which is coming from the other side. So this is actually a multi-input, multi-output system, and it's highly nonlinear. Okay, and if you want to compute, we can't do it in real time. So computation considerations, if you're talking about computation time, then it has been shown that for the Newton-Euler, so Newton-Euler, you require 126 into n minus 99 multiplications. Okay, and you need 106, where n is the degree of freedom, minus 93 additions. Okay, so for Newton-Euler, whereas for Lagrangian Euler, you require 32 into n raised to 4 plus 86 n raised to 3 plus 171 n raised to 2 plus 53 n minus 128 multiplications, and you require 25 n raised to 4 plus 66 n raised to 3 n raised to 3 plus 129 n squared plus 42 n minus 96 additions. Okay, for n is the degree of freedom of the system. So this actually gives us an idea of the amount of multiplications and additions are required for finding the dynamics, torque at the joints. And it is not possible to do this in real time. It's very clear from here. Okay, it will take some time, not real time. Now, it is known that for n is equal to 6, okay, the Newton-Euler is about 100 times more efficient than the Lagrangian-Euler. Equations. Okay, so this basically gives us two things. Number one, simulation. We'll come to that. When you have to simulate, you have to do the forward dynamics. Okay, and for which you have to do numerical integration, find the acceleration, and then from that integrate and get velocity, and then integrate again and get position. In terms of computational complexity, we have seen that our Newton-Euler is about 100 times more efficient than the Lagrangian-Euler, because in Newton-Euler the multiplications are much lesser. You can see that a very low number of multiplications are required. So today we will stop here. And in the next class we'll move on to trajectory planning, and then we'll move on to sensors, actuators, and controllers. So we'll stop here. Thank you.